On our first problem, we're asked to find the limit, assuming that we have this function. And really, if we remember our derivative limit definition derivatives, then this could be a little bit easier, but at the same time, we can also work this out. So either one would be correct. If we try to do our limit of what we're given, notice that this is going to go in place of f at x. So we're going to have the limit as x approaches 0, and we're going to have 2x squared plus 1 minus f at 0. So if I substitute in a 0 here, well then that's going to leave me with a 1 all over x squared. And again, we're just going to bring that x squared. So continuing on with our evaluation, the limit as x approaches 0, we're going to have the 1's to cancel. The x squareds will cancel of 2, which is just going to give us answer choice C. For our next problem, the graph of f is shown above. Which of the following statements about f is true? So we need to go through all the different statements. Now we are looking for which one is true, so we have to keep that in mind. Now for the first part, the limit as x approaches a is equal to the limit as x approaches b. I'm pretty sure that's not true because a is sitting here and b over here, that's not even going to be a defined limit, so I know a is not the case. Well, let's look at b. The limit as x approaches a is 2. So the limit from the left and the limit from the right are both approaching 2, and that is correct. Now do remember, even at a point of discontinuity, your limit can still exist. Alright, for our next problem, this is going to be a good problem. It looks like we might have to incorporate either L'Hopital's rule or something with this. Let's substitute in, though, for our first step just to make sure. So we're going to see that our limit as x approaches 1 of 1 over the natural log of 1. So that's really going to be 1 over 0, which is going to go back to our number over 0 equals a vertical asymptote here. And notice this is not a one-sided limit, so that's telling me that this limit does not exist. So for our next problem, the graph of f is shown above. Which of the following statements is, and now we're looking for a false statement. So for part A, f is continuous at A. Well, I think we found it right off because here we're not continuous at A. We have some kind of removable discontinuity there. So the answer for this one, very quickly we found, is A. Okay, for our next problem, here we're talking about a limit approaching infinity. If we're talking about limits approaching infinity, then we're really discussing the end behavior of this function. And if we're talking about end behavior, then we're talking about, let's see, we're talking about top heavy, or we're talking about bottom heavy, or we're talking about balanced. Yeah, L-A-N-C-E-D. I can't spell balanced today. So let's find our highest exponent and coefficient on top. So that's going to be 4n squared. And then on the bottom is just n squared. So notice the power here. This is balanced. And since it is balanced, then we're going to look at our ratio because they'll cancel each other out. And so that's going to leave us with 4. With number 6, it would be useful to rewrite this one and make it be the limit as x approaches 0 of x over and cosecant the reciprocal of sine. And when we do substitute in our 0, we're going to have 0 over 0. So what we need to do now is look at L'Hopital's rule And we're going to approximate this limit by looking at the derivative of the top over the derivative of the bottom. And when we do that, we have 1 over 1, which is 1. Number 7, a couple of ways you could do this one. One way would be L'Hopital's rule. The other way would be a means of factoring. Both are correct, whichever one you choose. So if we chose L'Hopital's rule, which I have a feeling that more people would probably choose that method, which is fine. If we substitute a in for x, we're going to have a squared minus a squared over a to the 4th minus a to the 4th. And that's going to give me 0 over 0. So if we approximate this with L'Hopital's rule, do keep in mind the a's are constant values, so they will cancel out. So I have the limit as x approaches a at 2x over 4x cubed. And when we simplify this down, notice that we're going to have 1 over 2x squared. And if I substitute my a in for x squared, I'm going to have 1 over 2a squared. That's going to give us answer choice B. For number 8, we have to remember what all of this asymptote information implies. Usually the first one to try to conquer would be the vertical asymptote, because that comes from setting the denominator equal to 0. So a couple of ways you could set this up. Take your denominator that you're given, set that equal to 0, and see that x equals negative c, but you're also told that x equals negative 3. So negative 3 would have to equal negative c. So we now know that c is 3. Now the other side of this, the horizontal asymptote, that's the same thing as your end behavior. And it's also the same thing as your top heavy, bottom heavy, and balanced. And out of those three, the only one that ever gave us a numerical value other than 0 would be our balanced. So let's look at our balanced, which is going to be these two. So I know that ax over x had to have been equal to 2. And so very quickly we see that a has to be 2. And we needed the sum of a and b, or a and c, sorry. So that sum is going to be positive 5. So for our next question, let g be a continuous function on a closed interval. We know a value for g at 0 and g at 1. Which of the following is not necessarily true? Well, I would go ahead and sketch. We know 0, 1. We know that's an ordered pair on our graph, and we know the graph 1, 0. Now, it's tempting to draw a straight line through those, but our graph does not have to look like that. It could be something to look like this. We don't know. All we know is that we have two values here and here. We know that right through here is connected. And so that's really all that we have. So let's look at what we do know. This, and we are continuous function on this closed interval. So look at A. There exists a number h between 0 and 1 such that g at h is bigger than g at x for all x inside that interval. Now that's kind of a lot of assumptions there. I don't know about that one, because it's saying this has to be bigger than the actual function. Well, this sounds like that we're talking about extrema, and so we don't know that much about it, so that's going to be probably not. Part B, for all a and b in the interval, if a equals b, g at a equals g at b. Well, not necessarily. We don't know that, so they're going to make it sound good, but I don't think that's going to be true. Let's see, part C, there exists a number h, so that g at h equals 1/2. Well, now that sounds almost tempting, because we have between 0 and 1, and we know from here and here. Let me change colors. So we know just this portion here to here, and here to here. This is all we know. And we know from 0 to 1. And we also know that from 0 to 1 on this side. So in part, let's see, part C, there exists, okay, that equals 1/2. So that one might be interesting to see. That's a possibility. Part D, there exists a number H. So that between 0 and 1, such that G at H equals 3/2. So 3/2 is really 1.5, isn't it? So now that we don't know, and I'm going to say we don't know because that 1.5 is way up here. The highest we could go was 1, and the farthest right we could go was 1. Well, 3.5 is up here somewhere, and that one we pretty sure that can't happen. We know that for sure. So not necessarily true. That's going to have to be answer choice D because it's outside of our y interval, so to speak. All right, so for number 10, we have a function. The limit as x approaches a of that function is equal to L. Which of the following must be true? So, it's tempting to say that, well, we know A doesn't necessarily have to be true because the limit and the derivative, if you know the limit, doesn't mean you know anything. We're tempted to say this one, but if we keep in mind, a limit can exist at a point of discontinuity. If you have a removable discontinuity, that limit's still going to exist. So that's not going to be true. Well, f of x is defined at x equals a. Well, not necessarily. I could do that. So C is not right. F at a equals L. Well, no, we just showed that. So it's going to be answer choice E. Not all of those have to, none of those actually have to be true. Okay, so number 11 seems very similar to some of the previous problems. Again, we have a limit that equals 7. X is approaching 3. But again, we don't know any of those have to be true. So it's going to be A. Right, and then for number 12, we're looking at the intermediate value theorem, which means if you see intermediate value theorem, we are looking or look for y values between, and look for what y values you're given. Your y values that you're given would be -1 and 3. And so right away, notice it says f at c has to equal 1 and f at c has to equal 0 and f at 0 has to equal 0. Now the intermediate value theorem says nothing at all about a derivative, so you can go ahead and throw that out. And if we do a quick sketch of the information given to us, we see for -3, we're at -1. So we know that's true. And then we know at +6, 3, 6, we're at +3. And we know our function is continuous, so we know something has to happen. And so what does the intermediate value theorem guarantee? Well, the highest y value that we have is 3, and the lowest y value we have is -1. So it's saying for some y value between -1 and 3, there has to be some x value or some c value in here that's going to give you a y value between those two numbers. So between -1 and 3. So let's look at the conclusion at some of these. Now A, no, we don't know f at 0 has to equal 0. Nowhere does that say that. So for part C, it says for my y values between -1 and 3, okay, for all x between -3 and 6. Well, Negative 3 and 6, that's our x value. So I don't think our intermediate value theorem talks about anything about x values. And again, D, same thing. So now let's look at E. I believe E is going to have to be it. One thing for sure, negative 1 and 3, well, that matches our y values. And it's saying that there has to be a c value so that my function crosses the x-axis. Well, yeah, that has to happen because I have a negative and a positive y value. So that's going to be answer choice E. All right, so for this next problem, it looks awful intimidating because it has so much stuff involving natural log. But the whole idea of a limit never changes here. So we have to look at the limit, since this is broken apart into a piecewise function. We look at our limit as x approaches 2 from the left of our function. And we have to look at our limit as x approaches 2 from the right of our function. And we have to see, do these things equal each other? Well, from the left, it's going to be less than, so we're going to substitute in here. So that's going to be the natural log of 2. Over from the right side, which is going to be this second portion, that's going to be 2 squared, which is 4, times natural log of 2. Well, we certainly don't have an exact value for natural log, but we know natural log of 2 is not the same as 4 times natural log of 2, hopefully. And so those aren't equal to each other, so that limit is not going to exist. All right, for part B, we are asked if k is a positive integer, then what is this limit equal to? So k is a positive integer. Well, this is one where we have to figure out which one has more power, because we're looking at our limit approaching infinity. So let's see if we can reason through this one. All right, so we're approaching positive infinity. So we have the limit as x approaches positive infinity of x to the k over e to the x. So, wow, this one, let's look at this. So this is going to be big raised to k, but now this down here is going to be e raised to the big power. So really big, that's just going to be some finite number, I would think. So again, this is just the idea of a very large number, and k is a positive integer. So really, this number here is going to stay the same. It's big, but it's not changing. Not really changing a whole lot. But if you look in the denominator, this is going to be 71828, my goodness. But that's raised to a really big number. And so I wouldn't hesitate to say this denominator is much larger than the numerator. So this is going to approach 0. Okay, so for our next question, it's a question about differentiable and continuous. So the first thing is continuity, or continuous comes before differentiable. So the first thing that we have to do here is check for continuity. So we're questioning at 3. So the first thing is f at 3 defined? So we have to look to see. And it's or equal to, so it is. And then the second thing is, let's check our limit. So the limit as x approaches 3 from the left of our function has to equal the limit as x approaches 3 from the right of our function. All right, so let's go substitute in. The limit from the left is going to be 3 squared, or 9. The limit from the right is going to be 18 minus 9, so that is 9. So that checks out. And so the third thing is, does the limit as x approaches 3 of the function equal the function's value at 3? So we saw that our limit value was 9, and the actual function's value is also 9. So we are at least continuous, so we can throw out A. Well, C is not going to make any sense. And D. So what's left for us to do is check to see about F prime and the limit from the left or right of F prime. So our F prime is going to be 2x for the top. For the bottom is going to be 6. And we need to check to see about our x value. So again, we look at the limit as x approaches 3 from the left of our function, or F prime. Does that equal our limit from the right? So I'm going to slide my screen over. The limit as x approaches 3 from the right of our derivative. So plugging in, again, that 2x came from the left, and if we plug in 3, we're going to have 6. Does that equal the limit from the other side? And the answer is yes, it does. So this is both continuous and differentiable. So this is going to be answer choice E. All right, so for part D, we want to know which of the following functions are continuous at x equals 1. So let's go substitute in some values and see, because that's going to be really the quickest way to see whether or not we are continuous there. So let's see. For the first one, do I know a natural log of 1 value? Well, yeah, natural log of 1 is 0. For the second one, e to the first is just e. And then for the third one, we have the natural log of e to the x minus 1. And so x is 1, so e minus 1, that's also going to be a defined value. So for all of those, it looks like we are going to have for sure values at 1. So our answer choice here is going to be E.